Hello students, now we solve question number 40 from the question series of IIT JAM 2024 mathematics question paper, and this question is given in section B, and here one or more than one options are true, and this question is based on group theory and real analysis. The question is, consider G equal to m plus n root 2 such that Mn belongs to Z as a subgroup of the additive group R. That means Z is the set of integers and R is the set of real numbers. Which of the following statements is or are true? Option A, G is a cyclic subgroup of R set of real numbers under addition. Option B, G intersection I is a non-empty for every non-empty open interval I subset of R. Option C, G is closed subset of R. And option D, G is isomorphic to the group Z cross Z, where the group operations in Z cross Z is defined by m1, n1 plus m2, n2 is equal to m1 plus m2, n1 plus n2. So let us try to solve this question. Here the given group is set of real numbers under addition, and the given set G is equal to m plus n root 2 such that Mn belongs to Z, set of integers, and the set G is a subgroup of R under addition. So G plus is a subgroup of R plus. To solve this question, we have to know the statement 1, any subgroup of R plus, that is any subgroup of the group of real numbers under addition is either cyclic or dense in R. That is, any subgroup of R plus is either cyclic or dense in R. And statement 2, the set m plus n root 2 such that Mn belongs to Z, set of integers, is dense in R. Here we do not solve the statement 1 and statement 2. We will solve the statement 1 and statement 2, and we will make another video. There we solve statement 1 and statement 2. So here we simply apply these statements. So in statement 1, any subgroup of R plus is either cyclic or dense in R. And statement 2, the set m plus n root 2 such that Mn belongs to Z is dense in R. So from the statement 2, the set is G, given set G is equal to m plus n root 2 such that Mn belongs to Z is a subgroup of So since it is dense in R, so G cannot be cyclic subgroup of R. So option A is false. Option A is false. In option B, G intersection I is non-empty, means every non-empty open interval I intersection the set G is non-empty. That means every point of R is the limit point of G. That is G intersection I is equal to not is equal to phi. That is for every non-empty open interval, for every non-empty open interval I subset of R. So in every open interval in R, intersection G not equal to null set. That means in every open interval I there exists an element G or X in G. That is every point of R is the limit point of G. Therefore closure of G is equal to R. Hence G is dense in R. Therefore option B is true. We will make another video and there we will prove the statement to the set m plus n root 2 such that mn belongs to Z is dense in R. So that part we will prove in another video, and also we will make another video, and in that video we will prove the statement 1: any subgroup of R plus is either cyclic or dense in R. So here the option B is true. Since closure of G is equal to R, but closure of G not is equal to G, so G is not closed subset of R. Because we know that the definition of closed subset of R, that is the closure of the set is equal to the set itself, then this set is closed. But here the closure of the set G is equal to full R, but closure of G not equal to G, so G is not closed subset of R. So option C is false. For option D, we will prove the group G plus isomorphic to z cross z under addition. Now we define a homomorphism phi from Z to Z cross Z defined by phi of m plus n root 2, the elements of G, is equal to m comma n. This belongs to Z cross Z because m belongs to Z and n belongs to Z. Now we prove phi define a homomorphism and it is injective and surjective. That means it is bijective homomorphism and therefore it is an isomorphism. Now m1 plus n1 root 2 belongs to Z. Then phi of m1 plus n1 root 2 is equal to m1 comma n1, and m2 plus n2 root 2 belongs to G. Then phi of m2 plus n2 root 2 is equal to m2 comma n2. Now phi of m1 plus n1 root 2 plus m2 plus n2 root 2 is equal to phi of m1 plus m2 plus n1 plus n2 root 2 is equal to m1 plus m2 comma n1 plus n2 is equal to m1 comma n1 plus m2 comma n2. That means phi of m1 plus n1 root 2 plus phi of m2 plus n2 root 2. Therefore phi of a plus b is equal to phi of a plus phi of b. Therefore phi is a homomorphism. Now kernel of phi is equal to m plus n root 2 belongs to G such that phi of m plus n root 2 is equal to the identity element of the group Z cross Z under addition, that is 0 0, is equal to m plus n root 2 belongs to G such that phi of m plus n root 2 is equal to m comma n is equal to 0 0. That means m is equal to 0, n is equal to 0, that is 0 0, identity element. Therefore phi is injective. Therefore phi is injective, and for every element m comma n in Z cross Z, there exists an element m plus n root 2 in G. Therefore phi is surjective. Now for every element m comma n belongs to z cross z, there exists an element m plus n root 2 belongs to G such that phi of m plus n root 2 is equal to m1 comma n m comma n, that is in every element in Z cross Z has pre-image in G. Therefore phi is surjective, that is now phi is homomorphism and phi is injective as well as surjective, therefore phi is bijective, that is phi is an isomorphism. Therefore the group G under addition is isomorphic to the group Z cross Z under addition. Therefore option D is also true. So here option B and option D are true and option A and option C are false. And we make another video to prove the statements, statement 1 and statement 2. Statement 1 we use here statement 1 and statement 2. Any subgroup of R plus is either cyclic or dense in R. That is, if one subgroup cyclic in R, that is not dense in R, and if one subgroup is dense in R, then this subgroup is not cyclic subgroup of R. That is, a subgroup cyclic in R but not dense in R, and a subgroup dense in R but not cyclic in R. And the set, the given set m plus n root 2 mn belongs to Z is dense in R. We will prove and make another video. Thank you.